In this video, we're going to review the find the volume of a solid. So there are 4 different techniques that we learned in the class. So so let's go one by one quickly. The formulas. So the first one is like a what we normally call the slicing method. So you place the object on the XYZ space, and then what we do, we're gonna cut it perpendicular to one of the axes. So let's say you cut it perpendicular to the x-axis, and then so you're gonna get the cross sections like that. So these are the cross sections. You cut it perpendicular to the x-axis, and then if you know this area, let's say you know this area, the typical area. So this is the area at the x position. Uh, so if you know the area, so let's call this area is x. So it's a function of x because it depends on x. So it's going to go through between a and b values. So the volume is simply going to be, so you just integrate this, just add all those small slabs or the slices. So you add them from a to b. Integral means the addition. All those small slabs. So this is the area of a slab, and this is the width of the slab, and then this is the volume of a slab, just a small volume. So the volume of one of those volume of one of those slice. So you can say slab also, slice. Okay, so that's the idea. It's a very simple idea. You cut it perpendicular one of the axis and then add them. And then what happen next, like when you have special different like structures, like for example you have volume of a revolution, like you have a curve or a region and you rotate about axis. So when you do those kind of things, so you have a region and you rotate about axis, so it's going to create there's some kind of symmetry. For example, if you cut it, now you either get a disc or a washer, because there's a rotation, so because of that you either get a disc or a washer. And then also in certain situations you can also get a cylinder. So let's see how to do what are those formulas. So the next one is the disk method. Let's say you have a curve like that, and then you can rotate about the x-axis. You can rotate about any axis, but just for simplicity we just x-axis. So what will happen when you do that, you can see it's gonna jump to the other side because of the rotation. So you're gonna get, so your solid looks like this. And then what happened when you look at the cross section, uh, they have a special format. So if you know this curve is y equal fx, so what will happen, if you cut it perpendicular to the x-axis, always cut perpendicular to the rotation axis. So what will happen is you get disc now. So you get like a disc. So that's what happens. So you get like a small disc like that, and then you can find the area. So that is what you get. So that's the disc you're gonna talk about. And then so what you need is just the radius. So if you know this radius r, and then you can find the area of this disk, and then you're going to add the disk. So that means in this case what will happen, the ax is simply going to be, because it's a circle, it is going to be pi r x is a function of x squared. So that's the area. So now what we're going to do, we just add them. We add all of those areas. So that means the volume is going to be pi. We can take, it's a constant to take it out, whatever the limit a b. So this is a radius squared dx. For simplicity we can write it like that. So that is the formula for the disk method. So the third one is the washer method. So let's talk about the third one. So what will happen in the third one is very similar to the previous one, but like there's a, like let's say one curve is like that, the second curve is like this. So when you rotate those two curves, now what happen, you can see it's going to jump to the other side and go like that. But so this is the how the solid look like. So that's a solid look like. And then what you can see now, when you cut it perpendicular to the axis, you're going to see there's a hole in there. So there's a part there and there's a part missing, and then there's a part there. Because of that, now they looks like so these are, it's going to create washers, because there's like a part and then there's a part missing. So it's going to create washers now. So that means we need to find the area. So you can see in the washer there are two radii. So there's one radii is a large radii. Let's call it capital R. And the small radii, so it's called small r, or lowercase, uppercase and lowercase. Because there's a correspondence, so it's easy to remember that. So that means in this case the formula going to be is very similar. It's an adjustment of the previous one, the disk method. but we have the area now going to be is again A to B, but you get the larger radius, let's get the large circle minus the small circle. When you subtract the two, you can see you get the shaded region. So that's the formula for the washer method. And then the last one is the disk method, the cylinders methods. So how the cylinder method looks like. Cylinder method is very important sometimes because there are certain problems. It's very hard to use the washer method for those problems. So let's say you have a region like this, and let's say you can rotate it about the y-axis. So what will happen when you rotate the y-axis? It's going to jump to the other side. So that means solid gonna look like this. So solid will be like that, and then you can see it is really hard to use the washer method now, because if you cut it perpendicular to the axis of rotation, you get you need to find so what will happen is you need to know these two and this one and that one. So that's what you get, but you need to know these two radii. One radii is small r and the large radii, but the problem is we don't know how to find that now for this one because it's the same curve. So that means for these situations we are not going to use the washer method, but we're going to use the cylinders method, or some also called the shell method. So we have this region. So what will happen is, so you can rotate, and then what we do, we're going to cut this into shells. So let's say this is the wall of the shell. So we're going to cut it like a small cylinders like that. So we call this a shell. So and then this is going to go like that. That's the border. So that's the what it looks like, and this is the edge. So you can see you have like small shells like. So they have a thickness. So that's the thickness of the shell. So that thickness go around, and so that's how we look like. So that's the shell you are talking about. Now what we do, we're gonna cut this whole region into those small cells and get the volume of one shell. So this shell has a radius, and this shell has a height. So that means if you know that, then you can actually write the formula. So you can see volume of one of those small shells, and you can see the thickness is a dx thickness. So you can see the thickness is this one. So it's a dx one. So it is a dx thickness. So that means the volume of this one of those shell is we can call this delta V, small volume, which is simply 2 pi r is the perimeter. If you multiply by thickness, you get the area. So that's the area of one of the rim area, and then you simply multiply by the height to get the volume. So now this is the volume of the one of those shell. So this is shell volume. So what you're going to do now is you're simply going to add all of those shells to create the get the volume of the whole region. So it's a 2 pi, you can take it out, it's a constant, and then you're going to get whatever the limit of x, and then you have a r and a h and the dx. So that's the formula for the um, shell method. And then also it can be in the other direction also, y direction. Only thing is you need to represent everything in terms of y. In this case you represent everything in terms of x. When you write y, you write everything in terms of x. Okay, so let's look at the problems now. So let's go, let's try to find like a small, like a simple A volume using the slicing method. So let's look at this problem. So as the first problem, we can look at this one. So what it says that the base of a solid lies on the xy plane between the curves y equal x squared and y equal 2 minus x squared. So you have one parabola and one inverted parabola. The cross sections perpendicular to the base and parallel to the y-axis are semicircles. So if you cut the solid, the cross sections perpendicular to the base and parallel to y-axis are semicircles. If you cut it perpendicular to the base, you see cross sections looks like semicircles. So if this is the case, what is the volume of the solid? So find the volume. So let's try to see the situation. So we have two curves. So these are two curves. So one is y equal x squared the other one is y equal 2 minus x squared. So what it says, there's a solid, and if you cut it perpendicular to the base and parallel to the y-axis, so you cut it like that. So if you look at the cross section, so that's the y-axis. If you look at the cross section, so that means if you look from this side, so you may look at like, so it's going to look like this. So you can see, so we have this part and that part, and then if you look at the cross section parallel to the y-axis, so you may see like semicircles. As I say, like this looks like a semicircle. So like that. So everywhere, if you cut it, so look like a semicircle. So that means we only need to find this area of this one. Once you know this area, what we can do, we're gonna add them. So that means, so we need to find the area at the x position of that. And also we need to know what are these bounds or the corners. So for the corners, we can do something interesting. We can just set the two curves equal. So for the intersection points, we can set them equal. So you set them x squared, u equal to 2 minus x squared. So you get 2x squared equal to, so this says that x squared equal to 1. In other words, x equals to plus or minus 1. So that means 1 is minus 1, 1 is plus 1. So those are the intersection points. That's where the two curves meet. So we know that part. Only thing that we need to do is find the area of this cross section. So if you know the radius, so if you know this radius, if you call this A, and then we can actually find the area of this semicircle. So area of the semicircle going to be 1/2 pi a squared. So only thing that we need to know is what is A. So so we need to find A. So A is the radius. So radius is, you can see, that is the half of the distance between the two curves. So you can see this length is 2a. So what you want to do is you need to get the half of that. So that's very easy to find because you know like one curve. So that means A is simply going to be according to the figure. So you can see it's half of the top curve, which is x squared, not x squared, it is 2 minus x squared. That's the top curve, 2 minus x squared. And the bottom curve is x squared. So if you take the difference between the two and take the half of it, that is going to be the radius. So that means you can see, you can simplify it nicely. So half, and then this is 2 minus 2x squared. So 2 get cancelled. So you get 1 minus x squared. So that is the A. So that means since we know A, we can plug it in there, and then we can actually find the area. So area going to be, because of that, pi, and then A is 1 minus x squared, and then you square. So that's the area of one such piece. So that's the area of one such piece at the x position. Now what we can do to find the volume, so the volume is simply, you're gonna integrate these. So that means it's an integral from, you can see in this case you have to integrate from -1 all the way to 1, ax dx. That's the formula for the slicing method. So if you plug in, so you're going to get -1 to 1 pi 1 minus x squared dx. So this is not like a difficult integral. This is a very easy integral. So if you want to set up the integral, this is the integral. So if please read the questions. Sometimes in some exams they say set up the integral. You don't have to evaluate, just set up the integral. So if they set up the integral, this is the integral you wanna get, and you're not going to evaluate. But if you want to evaluate, then you need to figure out how to do it. But in this case, it's not that bad. You can see this is an even function. So this is an even function. Since it's an even function, you can use the symmetric argument. So it is going to be twice the half of the integral. So it is actually, you can take 2 pi because pi is a constant. So we can take it out. So it is 2 pi 0 to 1 because it's symmetric, and then 1 minus x squared dx. And then how we do something like this, you can see you're going to distribute. So if you distribute, you can see you're going to get 1 minus 2 x squared plus x to the fourth power, and this is a very easy integral. You can do term by term integration and see whether you going to get this answer. Actually, there was a typo. You can see we forgot the half. There's a half in there, so that means you need to divide this one by 2. So that means so it's a pi over 2. So that means so this 2 you have to cancel that 2. There's no 2 there. Okay. So finally the answer is 8 pi over 15. So you should get 8 pi over 15 as the answer. Okay. So this is like a you can see the cross sections are semicircles, but you know in some other problems you might see cross sections as squares or cross sections as equilateral triangles. So let's write those formulas also, just in case, like you know, if you need to know other things. So this is what happened for those cases. So if the cross sections are squares, and if we want to know the area, and we know this formula, so if the side length is a, you can say the area is a squared. And the next one is equilateral triangles. So the equilateral triangles has each side length equals to a. So if you draw the perpendicular, you can see this one part is a and half. This angle is 60 degree. So if you take the tan, you can see that this side is square root 3 over 2a. So that means we know the height, we know the length of the base. So that means area going to be half. Base is a. Height is square root 3 over 2a. This simplifies to square root 3 over 4a squared. So it's worth remembering this formula. If you want to find the area, if the cross sections are equilateral triangles, you can directly use this formula. Okay, those are 3 common ones, and other things you can actually derive depending on what you are given. So if it is, if you know that, maybe one more, right triangle. So let's say the cross section is a right triangle. So right triangle. So maybe a situation like this. So if you know that it's a right triangle, and then if you are given a, and this h has to be given because it's not, you cannot get that, and then you can directly write the formula a as half ah. So some information should be given. So those are like a few common cross section areas that you can ask for a problem like this. Okay, so let's look at the next one. So we move on to volume problems, other types. This is a slicing one, so let's do the other types. So we have the other type of problems now. So what it says that the region bounded by y equal 2x, and y equal square root x is rotated about, so you're going to get different axes. So in this case, x-axis, y-axis, x equal 1/4, y equal 1, like that. And then they ask you, because once you rotate a region about an axis, what will happen is you're going to sweep a region, an area around an axis. So that means it's going to create a volume. So that's what happened when you rotate a area around an axis, it's going to generate a volume. So we try to find that volume. And then you can see, so since you rotate about an axis, so you can see in the answer always there's a pi in the answer because the rotation. So now, so if you get a problem like that, and you can see there are 2 different curves, one is y equal 2x and the other one is y equal square root x. So the first thing we do is we want to find, and then you can see there's a region bounded by those 2 curves. So that's the region bounded by the curves. So the first thing that we need to do is we need to find the intersection point. So how to find the intersection point? We're going to set them equal and solve. So you set them equal, the 2 curves, and then solve. How to solve it? You square both sides and then bring it to one side and factor, and then each factor going to produce a 0. So the first factor tell you that x equals 0. The second factor says x equal 1/4. So those are 2 zeros, and we mark the 2 zeros. And then to find the y value, what are you going to do? You just plug in that x value into one of the functions. So you can just plug into one of the functions. Once you plug into one of those functions, you can see that you get 1/2 as the y value. Okay, so that's the starting point. Now what we're going to do, we can do one by one, and we can talk about the uh, rotation about each axis. So let's do the first one. So let's rotate the given region about the x-axis. So this is the region we have, and we can rotate about the x-axis. Once you do that, it's going to jump to the other side, jump below. So it's going to go like that. So that's the region. Now what we can do, we can cut it perpendicular to the x-axis. So once you cut it perpendicular to the x-axis, you're going to get something like this. That's the typical cross section at the x position. So, and if you want to find the volume of this one, actually you can do this problem in two different ways. One way is to do this using the washer method. You can also do this problem using the cylinders method. You can do both techniques to do this problem. But if you need the cylinders, if you use the cylinders method, you need to find extra information there. For example, you need to know what is the, we have solved for x. Here you know how to do that. So when you say, so the top curve is y equal square root x, the bottom curve is y equal 2x. So the y equal 2x. Okay. So what you want to do is, if you get a problem like that, you want to find the two radii for this one, and also you can see that this is a dx problem because the thickness is dx. So thickness dx means everything you need to write in terms of x. That's the idea. The thickness tell you what direction you're gonna write, what variable. So let's do that in this case. So this is a dx problem, that means everything you need to write in terms of x. And then you can find the two radii. So what are the two radii? You can see there are a small radius. That's a small radius. You mark from the axis of rotation. This is the large radius. So you can see the small radius is the y coordinate of the bottom curve. That's the y coordinate of the bottom curve, which is 2x in terms of x. The large radius is the y coordinate of the top curve, which is square root x. Now what we can do, so we have the both radii, we can try to plug into the formula. So we use, in this case, we use the washer method because it look like a washer. There's a hole in there. So the formula is v equal pi, whatever the limit. So it's a 0 to 1/4. So as a formula, it is a to b pi r squared minus r squared dx. So we plug in here. So when you plug in, it is pi. So it is 0 to 1/4. So large radius is square root x, so which is square root x squared minus the small radius is 2x, so which is 2x squared. And then dx. So that is the integral. So if you want to set up the integral, this is the integral. You're done with this one. And then, but here I'm going to talk about how to like kind of finish this integral quickly. It might take time, but I'm going to write it quickly. So if you want to go through the questions, please use the timestamp given in the description, so you can jump to the different problems quickly rather than like looking at all the details. If you don't want to do that, you can just do that. You can just look at the arrow below the video, and you can jump through the different problems. Okay, so pi, so what are you going to do? So it is 0 to 1/4, and then you can see you square. So when you square, you get x here, and then here you get 4x to the squared dx, and then you can see this is like very easy integral. You can very easily integrate this one. So that means it is pi. If you integrate, you get x squared over 2 minus 4/3 x cubed. And then what we can do, we're going to plug in 1/4 and 0. So if you do that, you get pi. I'm going to write the numbers and you can check whether you get these things. So you get 1 over 32 minus 1 over 48. And you can see that both of them are in the denominator. You can take 16 as a common factor out. So if you take pi over 16, you can see from the first one, you get 1/2, minus from the second one, you get 1/3, and this part going to simplify to 1/6. So that means it is going to be 16 times 6, which is 16 times 5 is 80. So you add one more 16, 96. That means it's going to be pi over 96. This is the volume, so we write unit cube. So that's how you kind of completely solve the problem. But in the exams, you normally like set up the integral, unless like it is like easy one. That's how we normally do. Okay, and then the radii are, these are the radii, so we find the radii. Good. So let's try to rotate about the y-axis and see how it's gonna work. So this is a region, and you can rotate about the y-axis. When you do that, this region gonna jump to the other side. So it's going to be like this. So you get that, and then again, so you can again use two different techniques for this problem again. You can use the washer method or the cylinders method. So we can rotate the region above the y-axis. You can do this problem in two different ways. One is the washer method and also the cylinders method. So let's do both methods and see how the formula is going to change. So let's do the washer method first. Actually, cylinder method will be easier. So I'm going to do the cylinder method first. So let's draw a typical cylinder. So this is the wall, one wall, and the other one. So it's a typical cylinder. So we're going to draw. That's a typical cylinder. So what we need to do is we're going to pick a general x, and then we are going to find the radius, and then you can see the radius in this case is going to be the x coordinate, and also we need to find the height. Height, the top curve is square root x, the bottom curve is y equal 2x. So that means the height is simply the difference between the y coordinate. That means in terms of x, it is going to be square root x minus 2x. So that is going to be the height. So now we know the height and we also know the radius. So we can write the formula. So that means the volume formula going to be now, it is 2 pi, whatever the limit, radius of the cylinder and the height of the cylinder and the thickness. You can see the thickness is going in the x direction. That's why we solve for x. So dx problem here. So it is dx. So let's plug in. So it is 2 pi. The x value is going from 0 to 1/4. And the radius is x. The height is square root x minus 2x dx. So that is the complete integral for the volume. So how to simplify? When we want to simplify, what we normally do is we can distribute this. So you can distribute. So it is 2 pi and 0 to 1/4. So if you distribute, you get x to the 3 halves minus 2x squared. And you can see this is a very easy integral to do. And if you complete the integral, you should get a 7 pi over 80 as the answer. See whether you get that after you simplify. And then unit is unit cube with a volume problem. So let's do the same problem now using the washer method. So we have the same region and rotate about the y-axis. So what we can do in this case, we can use the washer method. So if you do the washer method, you can see your typical cut going to be like that, and on this side it's going to be like this. So what we need is we need to know the and then you can see this is a dy problem because you see the thickness is along the y direction. So that means everything has to be in terms of y before you integrate. So so we need to know what is this. This is small radius, and you can see it is a x coordinate. So since we need the x coordinate, what we can do, we're gonna say this, the top curve is y equal square root x. So we can solve for x. So if you solve for x, you can see you're gonna get x as y squared. And then do the same thing with the bottom curve. So that means the small radius is y squared. Do the same with the bottom one. So this is the large radius, we use uppercase R. So this the bottom curve is y equal 2x. So if you solve for x, now it's again the x coordinate of the bottom curve, because now what we are doing is we are giving a typical y and find everything else. The last time what we did, we give a typical x and find everything in terms of that. Here we give typical y, find everything in terms of y. So that means we're going to solve for x. So once you solve for x, you're going to see that you get y over 2. So that is the radius of the large one. So that's the, so you can see everything you express in terms of y now. Everything in terms of y, because it's a dy problem. And the earlier one, you can see everything in terms of x, because it's a dx problem. So it's a dy problem. So now we can plug into the formula. So what the formula? So this is the Washer method formula. So it is v. So we can write it is v equal pi a to b large R squared minus small r squared. It's a dy problem. Dy. Why dy? The thickness. Thickness is dy. So let's plug in. So if we plug in, you can see pi. The y values are going from 0 to 1/2. That's the reason why we want to find those things. 1/2. 0 to 1/2. And then r. R is, large R is y over 2. So it's a y over 2 squared minus small r is r. Small r is y squared. So it's a y squared and dy. And then you can see this is not that bad. So it is y and 0 to 1/2. So you can see here you get y squared over 4. The other one is y to the 4 dy, and then you can actually simplify this one and you should get the same answer as the last time. But if you want to set up the integral, this is the integral you are going to get using the Washer method. So if you look at these two integrals, I mean they are both okay. One is, we can say like one is better than the other for this one, but there are some problems like actually in the second one you have to do something extra, but in the cylinders method you don't have to do extra, you have everything we need already. But for the second one, the Washer method, you have to solve for x. So that's the difference. Okay, so let's try to do the third part. So we try to rotate this about x equal 1/4 axis. X equal 1/4 axis. So let's do that. So this is a region, it's the same region, but now you rotate this about the x equal 1/4 axis. So if you do that, so you can rotate about this axis, what will happen? This is going to jump to the other side of the axis. It's going to go like that, and it's on the other side it's going to go like this. So this is the region we have now. So, and again, just to understand what's going on, let's try to do both methods here. So one method to do this is a Washer method. So if you do the Washer method, you can see the cut going to go like this. That's one, is the other one. And then you can use any sides to get the values. But since we have all the values on this side, I'm going to use this side to get the values. So we already know all, pretty much everything because from the previous problem. So so this is 1/2. And this is a dy problem. It's very clear. The thickness is a y thickness. So, and then we also know that from the previous one, this x coordinate is y squared. That's what you get, y squared. And this one was y over 2, again from the previous problem. So what we need to do is, we need to know the length, the radii from the axis of rotation. So the axis of rotation is the dashed line. So that means, so this is the small r. So what is this r? You know this length. This length is 1/4. So that means you can write the small r is simply going to be 1/4 minus the y over 2. From the geometry, it's very clear. And we do the same thing with the large r. So that's the large r. So large r is again with a similar argument. It is going to be 1/4 minus the other value. So it is y squared, because those are the x coordinate. That's why we subtract that. Okay, so we get the two radii, and then we can have the formula now. So it's V is simply pi. So the corresponding values, so CD, that we normally put CD for that. So it's R squared minus R squared. It's a dy problem. That's the reason why we solve everything in terms of y. And now you're going to plug in. So if you plug in, you're going to get pi. So it's a y coordinate going from 0 to 1/2. And the large R, which is 1/4 minus y squared, whole thing squared, minus small r is 1/4 minus y over 2 squared, and it's a dy problem. So that is the integral you get for the volume using the Washer method. So let's try to use the cylinders method and see what you're going to get. So again, we have this region. So we rotate about the 1/4 axis, x equal 1/4, and again it's going to jump to the other side. So because of the rotation. So now what we can do, we are going to make cylinders. But how you make the cylinder? When you do the washer and disc, we cut it perpendicular to the axis of rotation. But when you do cylinders, we are not going to do that. What we do, we're going to make cylinders with the same axis as the axis of rotation. So that's the idea. So we're going to make cylinders with the axis as the axis of rotation. So that's the typical cylinder going to be. So that's the typical cylinder. So normally in exams, you are supposed to draw this one. Okay, so let's try to find those values now. And then also notice the thickness is on the x direction. Now see that it's a x, not the height, the width is x. So again, we pick a typical x here, and then we try to write everything in terms of x. So you can see the radius. So how to find the radius now? So radius is so this is the radius of the cylinder. So we define this r in terms of x. How to do that? We know the total length is 1/4, and this is the x coordinate, this length, and you can see r is simply 1/4 minus the x coordinate. So that is the radius. How to find the height? Height is simple for this problem because the top curve is y equal square root x. The bottom curve is y equal 2x. So if you subtract those two, you get the height. So y is simply y coordinate of the top curve minus y coordinate of the bottom curve. So which is square root x minus 2x. So that's the height. So we find everything for this one, the radius and the height. Now what we're going to do is we're going to plug into the cylinder's formula. So the cylinder formula is V equal 2 pi whatever the x limit is going to be. So if we say a to b r h dx. So that's the formula. So let's plug in. So that means if you plug in, you get 2 pi. The limit is going to be, x limit is going to be 0 to 1/4. The radius we found as 1/4 minus x, and then we found the height, which is square root x minus 2x dx. So that is the integral for the volume using the cylinders method. And if you finish the integral, you should get pi over 960 as the actual volume for the problem. Okay, so that's how you do the problem using two different techniques and using the washer and cylinders with the different axes. So here the axis is x equal 1/4. So see, none of these works with the disk method, because if disk means it's the same the washer method, but you make the inner radius 0, so then you get the disk. So let's try to do the last part. You can rotate the same region about the y equal 1 axis. That's the last part. So we have the region. So we can rotate this about the y equal 1 axis. So let's say this is y equal 1 axis. It's not according to scale. So what will happen when you do that? You're going to jump to the other side. The curve going to jump to the other side. So you're going to get, so you get the region like that. You're going to reflect it across the y equal 1 axis. So let's try to use the, so again, you can use the cylinders and washers. And if you want to use the cylinders, you need to solve for the x coordinate. But let's try to use the washer for this time. So we're going to use a washer. So that's the typical washer. So what we need is the large and the small radii. So and then so you can see you need to get that from the axis. So that's the axis. So this is the small radius and this is the large radius. So what are the connections? And you can see this length is 1. So that means if you subtract the y coordinates, you're gonna get those two radii. So that means you can see the small radius is 1 minus the top curve, y top curve, which is 1 minus square root x. The bottom is 1 minus the bottom curve in this case. So it is 1 minus 2x. So those are the two radii. So once you know the two radii, and then you also know the limits is going from 0 to pi over 4. It's a dx problem. That's why we write everything in terms of x. So that's like a typical x here. So let's try the formula. So the formula is v equal pi 0 1/4, and then you get 1 minus 2x squared minus 1 minus 2 square root x, 1 minus square root x squared dx. And you can clearly see that this is the large radius, this is the small radius. And then how to simplify? Distribute and collect terms. So if you do that, you should get something like this. So pi 0 to 1/4. If you distribute and simplify, you should get 4x squared minus 5x plus 2 square root x, and then you can do the term by term integration, and then you can evaluate at 1/4. So once you do that, you should get 17/32 pi as the answer, which is unit cube, because it's a volume problem. Okay, so this is how you solve those problems using all washer and the cylinders method. So let's look at another problem now. So this is another volume problem. So what it says that the region bounded by y equal ex, y equal ln x plus 1, and the lines x equals 0 and x equal e is rotated about these four axes. So let's try to understand the question again. So we have so the graphs are, we have y equal ex, we know the graph of that. That's the y equal ex graph. And then we also have y equal ln x plus 1. We know the graph of y equal ln x, which is this one, which passed through 1. So this is y equal ln x. But what we have here is y equal ln x plus 1. So when you do plus 1, you know that it's going to go backward by 1. It's going to go to the left by 1. That means this 1 goes to 0. So that means your new graph is going to look like this. It'll be parallel to the original one, but it's going to go like that. So that means the new one going to go through 0 and then go like that. So that's the second graph. That is the y equal ln x plus 1 graph. Now what we're going to do, and then also now what we can see, we can see the other things. So we have the line x equals 0. X equals 0 line is the y-axis. That's x equals 0 line, pass through 0. And then we also have x equal e. So x equal e means like somewhere here. So you can say like this line. So that's passed through E, x equal E. Okay, so that's the region. So this is the region we are talking about. So we have this region, and we're gonna rotate this region around different axes. So and other important values, this is 1 here, and those are the values we have. And then so let's try, and then also this axis is, so this line is x equals 0 or the y-axis. So let's do one by one now. So let's go to the rotation about x-axis. So this is the region. So we're going to rotate about the x-axis. So this one jump to the other side. So that's what happens when you rotate, and then this is this line. So what method we can use here? So you can see that if you try to use the cylinders method, you can be in a difficult situation because it's really hard to find the height. Because what we know, when we cut the cylinders, we're gonna cut it the axis of the cylinder and axis of the rotation has to be the same. So you have to find the y, the height. It's really hard to find the height here because they are not like easy. So we can use the washer method for this one. So we're gonna cut along like this, perpendicular to the axis of rotation, and then we use the top curves to find the values. So we pick a typical x here, and then we're going to find all the heights and the two radii. So you can see those radii are very easy to find. So this is the y equal ex curve, this is the y equal ln x plus 1 curve. So it is very easy to find the radii. So you can see the smaller radii, that's simply coming from the bottom curve. So small radius is the y of the bottom curve, which is ln 1 plus x. And the large radius means this one, which is coming from the top curve. So it is y of the top curve, which is y equal ex. So it is ex. So these are the two radii. And also we know the limits, so we can write the formula now. So that means v equal pi, so it's going from 0 to e r squared minus r squared dx. It's a dx, you can see thickness is along the thickness is dx on the x-axis. So if you plug in, so let's plug in. So we have 0 to e, that's the limit of x, and the large radius which is ex. So if you plug in, you get ex to the square minus the small radius ln x. So it is ln x plus 1 ln x plus 1 to the square dx. So that's what you get. And you can simplify this a little bit. So you can say pi 0 to e. You can write this one as, when you square ex, so ex times ex means e to the 2x, because you add the coefficients or you multiply the two numbers here. When you have power for power, you multiply the two numbers. So otherwise it's ex times ex, that means e to the 2x. A minus, and the other one is minus, so you can see we can write this one as ln squared x plus 1. You can put the square there. Okay, so we can write it like that. So that is the integral that you get. So if you want to set up the integral, this is the integral you get. And I'm going to leave this here because this is like this is not an easy integral to do. I mean, you can do it. First one is very easy, but the second one you need to do the integration by parts. So you can integrate by parts to get the answer. So this is the answer. If you do this, this is the answer you're going to get. So see whether you can get this answer. So the answer is, for this one, so you get this long expression as the answer. So this was done using the integration by parts formula. Yeah, but in exams, like normally we don't ask these kind of questions. I mean, we ask the question, but we don't ask you to simplify it. We just say set up the integral. So set up the integral means like this step. So once you do this step, that's set up the integral. but this one like we normally do like in homework and other situations. Okay, so let's look at the second part. So in this part we rotate about the y-axis. When you rotate about the y-axis, this can jump to the other side, so you get the two curves and the region. So for this problem, so it will be easy to do the cylinders now. So we can do the cylinders method. So we're going to pick a typical cross cylinder. It's a typical cylinder here. So we have the rim and the base. So what we need is the radius and the height. So we pick a typical x, and the radius is going to be the x coordinate. That's very clear. And also the height is going to be the difference in the two y coordinate. So we can see so r equal x, and the h is the two y coordinates, so y top minus y bottom. So you can see you're gonna get y top is the ex, the bottom is the ln x plus 1. So we have all the information. Now we just need to plug in that into the equation. So the equation is volume equal 2 pi. So the limits going from it's the x limits, is because it's a dx problem. So thickness is the x dx. So it's a dx problem. So the x limits are 0 to e, and the radius times height dx. So if you plug in, you get 2 pi 0 to e. The radius is x. The height is ex minus ln x plus 1 dx. So that's what you get. And you can see that if you break it into two integrals, so you're going to get 2 pi. The first integral is 0 to e x ex. That's like a typical integral that you normally do using integration by parts. So the second one is 2 pi 0 to e x ln x plus 1 dx. This is also an integral we normally do using integration by parts. So we have to do two integration by parts to do this integral. So if you do it, if you call this is I1 and I2, the two integrals, if you call this first integral is, let's call this I1 integral, let's call the second one is I2 integral, and you can see for the I1 integral, what we can do, you pick u equal x and the dv equal ex dx. For the second integral, you can see this is a log integral. When you see log, we pick the ln part as the u. For the second one, we're going to pick u equal ln x plus 1 and dv equal, in this case, x dx. Yeah, so if you do those two, and you can get the answer for this one. So again, in the exam, we only ask you to set up the integral. So this is the set up the integral step. And then if you want to evaluate, so you can just use the integration by parts, and you should get this as the answer. So answer is, so this is what you get as the answer. It's a very complicated expression because of the log term and repeated integrals there. So, but this is what you get as the answer. But in exams, we are not going to ask you to do that. So we only say set up the integral. So setting up the integral is really easy, and you can see here. Okay, so let's move on to the next one. So we do x equal -2 axis now. So this is a region, and we can rotate this about the y equal -2 axis. It's not according to scale, so right there. So this region going to jump to the other side. So this is what happened. And then we can rotate this. So we rotate this actually about this axis. So so we draw the, so how we do, and if you try to use the washer method, it will be very difficult. We're going to use the cylinders for this one. So we're going to mark the typical cross section of the cylinder. So that's a cylinder, that's a cross section. So your cylinder going to go like this. and that's the rim of the cylinder. Good. And this is the base, the bottom part. Good. So what we need to do is we're going to find the so if you call this x, we want to find the radius, and you can see this length is 2. This is the x coordinate, so that means the radius, that's a radius from, we measure from the axis. So there's a radius. So radius is, you can see it is simply 2 plus x, that's the radius. The height is easy. The height is simply the difference between the two y values. So which is ex is the top one, ln x plus 1 is the bottom one. So now we have everything we need. So we can write the formula. So the volume is 2 pi 0e RH dx again. So if you plug in, you're going to get 2 pi 0e 2 plus x is the radius. The height is ex minus ln x plus 1 dx. So again, once you distribute it, you can do this problem using integration by parts. So I'm going to skip that part, rather it's going to be really lengthy. Okay, so let's look at the last part. In this one, we're going to rotate about the y equal -1 axis. So this is the region. So we're going to rotate this about the y equal -1 axis. So this is y equal -1. So then region going to jump to the other side. So for this one, since we rotate about this axis, so again we can use the washer or cylinder, but in this one it would be, so cylinder would be difficult, because when you want to find the cylinder, you want to find the height. It's very difficult to find the height. So we can use the washer method for this one. So we mark the typical washer, and then we're going to find the two radii. So this is the thickness is a dx1. So that means we need to find both everything in terms of x. And you can see that this length is 1. So the small radius would be the height of the bottom one plus 1. So this will be yb plus 1. So that means 1 plus, you can see the bottom curve is ln x plus 1. And similarly, the large radius would be, so this is a large one, and you can see it is again 1 plus the top one. So it's a y top plus 1, so which is 1 plus ex. So we know the two radii, and then we can write the formula now. So the volume is going to be v equal, so we're going to write here because like it's going to be a lengthy one. So the v equal pi, so you can see it is 0 to e, those are the x values. So r squared minus r squared dx problem. So if you plug in, you're going to get pi 0 to e. So the large radius is 1 plus ex. So we can square that, minus so a small radius is 1 plus ln x plus 1. So we can square that 2, and then we can integrate this one. And then you can see the first integral is actually really easy to do. You can just distribute and integrate. For the second one, you need to use the integration by parts. So I'm going to leave that. Okay, so this is how you do problems like this. Thank you so much for watching.